So let's start. And yeah, we start with properties of the limit for vector functions. So theorem 1 in this section, properties of the limit of vector functions. This theorem shows how to extend properties of sequences, of limit of sequences, to the case of limit of functions. So rather easily. First, suppose limit as t tends to t naught a of t equals to, let's say, a naught, limit as t tends to t naught b of t equals to b naught, then limit of the sum of those vector functions a plus b of t equals to the sum of limits. Second, suppose also limit of a vector function is given, and also limit of a usual function, let's say alpha of t, is also given. Then limit as t tends to t naught of the product of number times vector equals to alpha naught times vector a naught. Third, suppose limits, again like in first, we have two limits of vector functions. Then limit of the product, scalar product, is equal to scalar product of limits. A naught times b naught. Last property in R3 is valid only in R3. So if, like before, limit of vector functions in R3 now are given, then the limit of the vector product is given as a vector product of limits. So a of t b of t equals to vector product of limits. And proof is absolutely similar for each of those assertions. And let me emphasize an agreement which was made here. So you see, I didn't write anything else about the domain for each of those functions. So it means we suppose functions are determined in a punctured neighborhood, and of course they have, you see, to be able to add, they have the same dimension, of course. First, second, third, they should be in Rn. Sorry, for second we don't need to suppose anything else. And for first and third we need to suppose dimensions are the same. Otherwise we cannot form the sum or scalar product. And proofs are absolutely similar. So we use Heine definition. And then we proceed like that. So we need to take arbitrary sequence Tn, well, not n, let me, m, Tm, m from 1 to infinity, Tm not equals to T naught, and Tm tends to T naught as m tends to infinity. So we take arbitrary such sequence, and of course there is extra supposition. Tm are in the domain for each of those vector functions. And then how we proceed? We take, for example, for the first assertion. So we know that A of Tm tends to A naught, and B of Tm tends to B naught, as m tends to infinity by Heine definitions for each of those vector functions. And then we use property of limit, namely theorem 1 from former section, section 2, properties of limit for sequences, and we deduce that limit of the sum of those sequences is equal to the sum of limit. That gives the assertion. And similar, we can proceed for each of those of other assertions. So you see, limits for each operation, they are preserved. Okay, and also I need a definition in future, and as far as I know, you started, at least part of you started to study curves on seminars. Unfortunately, I'm a little bit late because of a lot of preliminary material which we need. So, definition. A curve in Rn is the image of an interval, let's say AB, in R under the vector function A, let's say, from AB of too many A's. Okay, let it be F. AB to Rn such that limit as t tends to t naught t in AB, f of t equals to f of t naught for each t naught in AB. That is what we'll call later f is continuous on AB. But in general, the definition of continuity will be given a little bit later. Before I want to learn more about limits. So, a little different order. So, okay. Now, let me give an analogous. So, we studied a little bit limits of vector functions. Now, let us turn to limits of functions from Rn to R. So, functions of several variables. Let me recall definition of limit. So, and maybe this is not a definition, better to say this is a remark. For the functions f from D to R, where D is in Rn. We write limit as x tends to x naught f of x equals to L, instead of limit as x tends to x naught and x is in D. If x naught is a limit point of D. So, if the domain of our function has x naught as a limit point, then we omit this condition and write like that, simply. Okay? So, it means that like for functions of one variable, we also didn't write here t belongs to the domain of a function. So we suppose that the point is a limit point of the domain. So the function is defined on a domain D which has x naught as a limit point. So, and then I can formulate theorem 2, which is similar. So properties of the limit of functions of several variables. First, if limit as x tends to x naught f of x equals to L, limit x tends to x naught g of x equals to, let's say, L1 here, L2, then limit, okay, A, limit as x tends to x naught f of x plus g f plus g of x equals to L1 plus L2. B, similar assertion for the difference. And for the product. F times g of x equals to L1 times L2. And second, if limit as x tends to x naught f of x equals to L1, limit of g of x equals to L2, which is not 0, then limit of the ratio f over g and x equals to L1 over L2. The proof is similar, and maybe I'll prove only second assertion. Proof for second, because it contains some additional considerations. So once again, we take arbitrary sequence m x m are not equals to x naught, and limit as m tends to infinity x m equals to x naught. And then as we know, limit of the sequence of values is equal to L1, and also limit of the sequence of values of g equals to L2. And now what's important, because of non-zero here, L2 is not 0, right? Then we refer to properties of sequences of numbers. So if we have sequence of numbers which has non-zero limit, right? Then, as we know, signs of those numbers are the same as sign of L2. So it means if L2 is positive, all those numbers are positive starting from certain number. For sufficiently large m, it means that for all m greater than, let's say, capital M, right? there exists such a capital M, such that all those numbers are not 0. That's important. So it means that we can form, so then limit as m tends to infinity f over xm, f of xm over g of xm is equal to L1 over L2, right? So you see, rigorously speaking, this ratio may be not defined for finitely many first terms, right? Because we cannot exclude g of xm is 0. It might be the case, but we can be sure that this sequence is well defined for sufficiently large m. And in this sense, we can say the limit of this sequence equals to L1 over L2. So it might be that this sequence is not well defined for first indices, right? It might be the case, but it doesn't matter for the limit. So that is an agreement which we make, in fact. And so you see, for arbitrary sequence, limit of this ratio is L1 over L2. It means we have this equality. So you see, Heine definition works very well to prove properties of the limit. Now I would like to discuss a little bit in more details the limit of functions of several variables. So, and I want to discuss it for the case, so suppose now n equals to 2. So it means we are talking about functions of two variables instead of x1, x2, x and y. Functions of two variables, right? Then we can consider also so-called iterated limits. So what are iterated limits? For example, limit as x tends to x naught, y tends to y naught, f of x, y, and also y tends to y naught, x tends to x naught, f of x, y. These are iterated limits, right? And also limit of a function of two variables, limit of a function of two variables as it was defined, limit x, y tends to x naught, y naught, f of x, y. So for functions of two variables, we can form several types of limits, right? And all of them, in general, are different. So what I want to say, they may be different. It might be that both exist and are equal, but this doesn't exist. But also it might be that this limit exists, but iterated limit do not exist. So all possibilities can be realized. And let me give a couple of examples. So example 1. F of xy equals to xy over x squared plus y squared for xy not equals to 0, and 0 if it is 0. So let us look at iterated limits. Of course, x naught, y naught is 0, 0. That is interesting point for us. So look what happens. And look at iterated limits. Iterated limits here are as follows. Same in other direction here. And look what happens here. For example, the first one. How we compute this limit? So, when we are talking about limit as x tends to 0, right? Then we are interested in the values of this object when x approaches to 0 but is not equal to 0. Remember, punctured neighborhood is interesting, right? Remember theory of usual limits. Yeah? So it means that we should suppose when we compute this limit that x is not equal to 0, right? So x is not equal to 0. Look, what happens with this then? So we look at the function, right? We suppose x is not 0. If x is not 0, then we are here, right? Look, x is not 0. That is the expression. X is not equal to 0, and we want to compute what happens when y tends to 0. And if y tends to 0, then answer is obvious. It's 0, right? So inner limit is identically 0 for each x which is not 0, right? Let me write here. Equals to 0 if x not equals to 0. Very good function, which is not 0, right? Sorry, which is equal to 0 for each x which is not equal to 0, right? Then the limit is certainly 0, right? As x tends to 0. So that is 0. But this limit doesn't exist. Why? Because, for example, by Heine definition, what means if limit exists? It means if we take a sequence xn, yn, which tends to 0, 0, right? And tends to infinity. Yeah, now I can use n because we are in R2. So, and I can choose the sequence, couple sequences. For example, one of them. First, xn equals to 1 over n, yn equals to 0. Then what happens with f of xn, yn. Look, yn is 0, right? Substitute, we have 0. Tends to 0, right? As n tends to infinity. Take another sequence. Xn equals to 1 over n, yn equals to 1 over n. This sequence of points definitely tends to 0, 0 also, right? Because of properties, remember. If we have vectors, vector tends to vector if components tend to components, right? Here we have component-wise. So 1 over n and 1 over n converges to 0, 0, component-wise. Hence, it converges as vectors, right? Now, what happens with f? What's with it? Substitute 1 over n, 1 over n. Here we have 1 over n squared, right? Here we have 2 over n squared, right? The result is 1/2, which tends to 1/2, right? And it means there is no limit, because the existence of such limit, according to Heine definition, means that for arbitrary sequence like that, the limit of f of xn, yn should be equal to this limit, right? And we have two different values for two different sequences, hence no limit. No. Okay, example 2. And here I'll define the function like that. That is square root of x squared plus y squared times sine 1 over x sine, maybe not sine, maybe it's better to take cosine. Doesn't matter. Sine 1 over y, when x not equals to 0 and y not equals to 0, right? And 0 otherwise. So the function is well defined everywhere, right? Now, look at iterated limits. For example, what can we say about this? So, I want to substitute x is not equal to 0, right? So let me look at this inner limit. So x is not equal to 0, right? So it means I'm interested in this limit, y tends to 0, square root of x squared plus y squared times sine 1 over x times sine 1 over y. Okay, so if x is not equal to when sine equals to 0, sine equals to 0 if this argument is pi n, so 1 over pi n, an integer but not 0, right? So if x is not like that, then what happens with it? This number tends to, as y tends to 0, square root x squared, so modulo x, right, times sine 1 over x, which is not 0, right, for this x, not 0. What happens with this? we know sine 1 over y has no limit, right? It alternates as we approach to 0, between -1 and 1, right? So it means that this limit doesn't exist. If x is not equal to this, right? And it means iterated limit doesn't exist as well, right? Because inner limit doesn't exist. Now, I want to prove that limit as a function of two variables exists. So, what is about limit as x, y tends to 0, 0 of our function? The best way to do it is, in fact, related to so-called polar coordinates. So, what they are? What they are? Polar coordinates. So x is, let's say, rho cosine phi, y is rho sine phi. So I take x, y is a point, that is rho, that is phi, angle phi. Polar coordinates. So let's substitute. What is our function in polar coordinates? That is, okay, that is rho times sine 1 over rho cosine phi, sine 1 over rho sine phi. If, okay, x is not 0, means rho not equals to 0 and phi not equals to, okay, I can exclude each of zeros on the place of x or y by that one, right? Integer multiple of pi over 2. If it is not integer multiple of pi over 2, then neither x nor y can be 0, right? So, and 0 otherwise. Okay, let's have a break. Okay, there is a question, what does the limit of function shows? And iterated limit. I'll try to explain it a little bit later. Okay. Now, let us return to our example. So, you see that we have an estimate which is valid for arbitrary phi, rho, and phi. The estimation is like that, right? Because model of signs are less or equal to 1, right? So we may forget about that. Now, I want to prove that limit as x, y tends to 0, 0, f of x, y equals to 0. Why? Because I follow Now it's better to use Cauchy definition. So what is it? By definition, for arbitrary epsilon greater than 0, there exists delta greater than 0, such that for all xy which satisfy the following restriction, I want to have f of xy minus 0 less than epsilon. So that is what I want to prove, right? Now, look. What is it? This distance between 2 points. We know what it is. That is square root of x squared plus y squared. Okay, I should write square root of x minus 0 squared plus y minus 0 squared, right? That is square root of x squared plus y squared. And that is precisely rho, right? So, now look. Here I have estimate, you see, f of xy is less or equal to rho, right? We proved it just now. So I want to have it less than epsilon. When it will be true? If, look, what I should suppose, rho less than delta, right? So I can choose delta equals to epsilon, right? So now look, for arbitrary epsilon greater than 0, I indicate delta, which is just epsilon, right? Such that for each point xy, which satisfies this inequality, and this inequality here reads like rho less than epsilon, right? But if rho is less than epsilon, then for sure modulo f of xy is less than epsilon, right? So we have proved. And also it indicates a practical way to prove limits of functions of two variables if you have some problems, right? So what you should do, you should estimate somehow by a function of rho without phi. That's the point. No dependence of phi. Why is this important? Because return to example 1. So example 1, revisit, right? Return to this example. Look, if we try to use the same idea with polar coordinates, right? What is f of rho cosine phi, rho sine phi? Substitute. We obtain rho squared cosine phi sine phi divided by rho squared. That is cosine phi sine phi, right? So you see, for some values of phi that is 0, right? But for other values of phi that is not 0 and doesn't tend to 0, right? That is why no limit in that case. And in fact, the best way to explain this phenomenon is to use so-called direction limit also. So for functions of several variables, I'll give the definition not in R2 but in Rn. Also, it is very convenient to indicate direction limit. So, definition. Let D be a vector in Rn. direction limit of f from D to R. D is in Rn. At x naught, which is limit point of D, in the direction of D is limit as x tends to x naught f of x, x belongs to D, where D is the set of vectors x in D such that x minus x naught equals to T D. T is positive. So it means you have a point x naught, you have direction, vector of direction, right? We have our domain D, domain of function, and we look only at this direction. So here we have, that is D. So we are interested in the limit only on this part. And lemma 3, I think, right? In this section. Lemma 3. Limit as x tends to x naught, x in, so limit, direction limit can be computed also as one-sided limit of a function of one variable, 0 plus f of x naught plus t d. I forget also to be a non-zero vector. Otherwise makes no sense. Non-zero vector, of course. Non-zero vector. Proof of this lemma is immediate. Because we write what means that one. So for arbitrary epsilon greater than 0, there exists delta greater than 0, such that for all x in dd with the following inequality, okay, length less than delta, we have inequality f of x minus L, where L is the limit, right? That is, let it be L, denoted by L, this limit. That is Cauchy definition for this direction limit. Now look carefully what is here. X in dd, what it means? X has the following representation, right? Where t is positive. Then what is it? X minus x naught is t times d, right? T is positive, so we can write here t times d, right? That is t times d. So I can rewrite, look, so the only restriction is less than delta, right? But then I can define delta 1 equals to delta over modular length of d, right? Then I can rewrite it as follows. Look, for arbitrary epsilon, there exists delta 1 positive such that for all t which are positive and less than delta 1, I have an equality modulo f of x naught plus t d minus L less than epsilon. Look, here I wrote a function of one variable t. All other things are fixed, right? So we have a function of one variable t. And what is written here is precisely the definition that this limit equals to L. So that's it. So that is about direction limit. Now I can formulate a theorem, which is number of that theorem. Theorem 3. If there exists limit as x tends to x naught f of x equals to L, then there exists direction limits of f at x naught in any direction d which are equal to L. So proof is immediate. So look, because if we know there exists a limit, so I can write what it means. For arbitrary epsilon, there exists delta, such that for all x which satisfy this inequality, we have f of x minus L less than epsilon, right? So here I have arbitrary x. In particular, I can put here arbitrary restriction to be x equals to, let's say, x naught plus td, right? Doesn't matter which d I choose here, right? So proof is immediate. But what is important? Look. Return to example 1 once again. What happens now? Direction d here is completely determined by the angle phi, right? By the angle phi. So what is about direction limit for this function from example 1? It's written here, right? This cosine phi sine phi is precisely the limit in the direction d with angle phi, right? I erased picture of polar coordinates, unfortunately. No. If we fix angle phi, then for arbitrary vector in that direction, we have this direction limit. But look, converse is not true. What means converse? So you can get an impression that if any direction limit are the same, then you have limit. That is not true. One more example. Example 3. F of xy equals to xy squared over x squared plus x plus y power 4. Is it? Okay, if it is not, I'll change it. Xy not equals to 0, 0, and 0 if this is 0, right? So direction limit, how we can compute it? It means, what is direction limit here? We approach to 0, so take arbitrary direction. To take arbitrary direction, we choose angle phi, or in other words, we substitute y equals to kx, right? So let's substitute f of x, kx. So what is it? That is k squared x cubed over x squared plus k power 4 x power 4, right? So yeah, it works. It works if x is not 0, and 0 if x equals to 0, right? Now look what happens. We can cancel x squared, right? And what remains? We have x in numerator, right? And 1 plus x squared times something in denominator, right? So it means we have limit 0 as x tends to 0, right? And it means that we have limit in any direction equals to 0, but it has no limit. Why? Because look, if I choose xn equals to 1 over n squared and yn equals to 1 over n, then of course this sequence tends to 0, right? But what is about f of x n yn? Substitute 1 over n squared times 1 over n squared, 1 over n power 4, right? In denominator, 1 over n power 4 plus 1 over n power 4, 2 over n power 4. So 1/2 doesn't tend to 0, right? And so no limit, right? So limit in arbitrary direction is 0, but no limit as a function of two variables. And this is typical example. So how to solve if your function has no limit as a function of two variables? D1. D1. Where is D1? Delta 1. Delta 1 is here, right? That is just to repeat. So here we had an inequality for x. I want to have an inequality for t. Here. Now, look, that is so-called two-path test. If there are two path curves in R2 such that limit of f of x, y along those paths are different, then the function has no limit. So that is not a theorem, that is just description of this test, right? So how it works rigorously? So look, I look at this function, right? So when I approach along arbitrary line, the limit is 0. But if I substitute x squared equals to y, like that, y equals to x squared, right? Like that. So if I approach to 0 along this curve, right, then what happens? Substitute here. No, x, sorry. It was wrong, sorry. Y squared equals to x, right? Like that. Yeah, like that. I'm sorry. X equals to y squared, right? Then what happens? X equals to y squared, y4, and here 2 times y4, right? So 1/2. So values along this curve are equal to f here is 1/2. So the limit along this curve equals to 1/2. Limits along arbitrary line equals to 0. So no limit. No. Now I can explain a little bit about what is the limit, direction limit, and so on, more geometrically. So what we have? We have, if we are talking about a function of 2 variables, then we can imagine a little bit the picture. For more general case, it's impossible, of course, but if we have a function of 2 variables, right, that equals to f of x, y. That is model case, right? When we can represent the graph of that function, right? In example 3, we took y equals, so y is one of our variables. No, y is not a function of x. Both x and y are independent variables here. Y is not value of function, no. Like here, I don't know, that equals to f of x, y. So x and y are both, why does it not indicate it? Why? That is, you are perfectly right when you indicate there is a question that when I choose y equals to kx, then there is a dependence between them. That is precisely the case. That is how this test works. So if we are talking about limit of a function of 2 variables, then we suppose that both variables are independent. So they may vary in arbitrary way, right? and it means if there exists a limit, then we can vary x and y in arbitrary way, and the same value exists, right? But if this is not the case, then what happens? We can choose such a dependence between y and x, that is a path, a particular case, right? Such that along this way, the limit is different. The limit is different, right? So look, usually when we are talking about function of two variables, then we can represent it. I mean, graph of that function. What is it? Oh, it's worse. So the graph of that function can be represented as a surface, right? So we have a domain where our function is defined, and for each point in that domain, we indicate here over that domain, we indicate some, let's say, yeah, that is a surface, right, over this domain, yeah, like that, something like that, right? So it means, not precisely, okay, like that, like that, like that, and so on. Now, so for each point here, and in particular, I'm interested in if I talk about limit at a point, right? Then what it means. So here I have the limit, right? What it means. Why this is the limit. Doesn't matter how I approach in the plane, right? Xy is in the plane. The values of that approach to that one, right? If graph is like that. Here, of course, I will not try to draw the picture of the graph of that function. I guess you can do it by yourself. There are a lot of tools to draw it, right? So this is not like that. This is very how to say, breaking, right? Breaking surface, very breaking surface if you approach to 0, right? So in fact, you see, I can choose y squared equals to kx, and it gives you arbitrary value. So if you approach along different parabolas, you obtain different limits. That's very crazy graph, right? If you try to do it. And of course, in the best case, when we have picture like that, I mean, surface is smooth. I don't want to give precise definition of smooth now, but in that case, everything is very good, and you will not meet with such strange examples, right? Those examples usually do not appear in practical things. In practical things, usually you have smooth surfaces, and you don't care about limits and so on. But you see, sometimes it might be even such a simple function, right? But very strange behavior. Yeah, that's it. Okay, so I think that's all what I wanted to say about limits. Yeah. Now, section 4, continuity. Section 4, continuity. So I want to discuss now continuity once again in more general case. So we start with functions from D to Y, where D is a subset of X, X, Y are metric spaces. Definition. So that is general situation. We are talking about a function from one metric space to another. Definition. If x naught in D is a limit point of D, then f is called continuous at x naught if too many ifs. Okay, let it be 4. For limit when limit as x tends to x naught x in D, f of x equals to f at x naught. So for limit point, continuity means the limit equals to the value of the function, like here, right? But for example, I can choose the situation. For example, let me make a puncture. So suppose that the value of that function at that point is equal to 0, right? So I make a hole in this surface, right? I change the value of our function at one point only, right? Let it be, let's say, 0. Then what's about limit? Limit is still the same, right? Because when we compute the limit, we are looking only at the values in a punctured neighborhood. So the limit is different, right? Sorry, the limit is the same, right? But the function now is not continuous at that point, because the limit does not coincide with the value of the function. So continuity is when the value coincides with the limit. For example, example 1, of course, no continuity because no limit, right? Example 3 also no continuity because no limit. But example 2 continues, because in example 2, if you look at your notes, example 2, we have limit equals to 0 and the value of function was 0. So example 2 from former section is an example of a continuous function at 0. Okay, and now I can give two definitions. So definition 1 makes no sense because I'll need to repeat them next time, but nothing to do. So f is continuous on D if it is continuous at all limit points of D in D. Okay, maybe it sounds not good. Limit points of D in D, right? Why? Because limit points of D need not to belong to D, right? But we are talking only about limit points of D which belong to D. Other limit points are not interested. Also, we are not interested in isolated points. That's also important observation. So look, what's important. Okay, maybe I'll stop on this place. Why I indicate here definition 1? That is definition 1 of continuity. There will be another definition 2 of continuity next time, which is equivalent. And now I want to discuss a little bit this definition. So if x naught is an isolated point of D, then f is continuous at x naught. That is, how to say, you can take it as an agreement, or that is a corollary if we are talking about. So look, if you have an isolated point here, right, then according to that definition we are not interested in the behavior of our function at that point, right? So because here we ask something only for limit points, right? For isolated points we don't care absolutely about the behavior of a function. Example of what? Remember, there was an example, you remember, point 1, 2, 3 intersected with q and so on, and there was 1.1, right? So if you have a function which is defined somehow on interval, let's say 2, 3, right? And you have also to your set D, you add 1.1 somewhere far from this interval, right? It doesn't matter what is value of that function. In any case, the function will be continuous on the union of interval and that isolated point. That is important. So when you are talking about continuity and a point is an isolated point of the domain, it doesn't matter what is value at that point. Every function is continuous at isolated point. That's it. Okay, there is a question. What is the difference between the definition of continuity and the definition which says a curve, etc.? Yeah, in fact, the definition of the curve was just about this continuity. Yeah, it was a particular case. So curve is a mapping from closed interval to Rn. Very particular case of this definition. Yeah. Okay, thanks for your attention. Sorry.